Boa tarde, pessoal. E aí, tá todo mundo beleza? Como foi a praia hoje de manhã? Tava boa? Eu só queria dar um aviso antes da gente começar essa keynote. Ainda temos senhas do jantar oficial. Temos, para ser mais preciso, 12 senhas. Então, quem ainda não comprou e tiver interesse de ir, pode passar amanhã no primeiro coffee break da tarde. Nós temos 2. Passar no primeiro, que é de 2h30, 14h30. E o valor é R$90 para quem ainda não sabe. Vai ser no Camarões Restaurante. Está incluído a comida, alguns pratos lá que a gente selecionou, bebida não alcoólica, café, suco, refrigerante. Então, quem quiser ir para o Camarões amanhã com a gente, passa lá na secretaria, tá certo? Vou passar agora para a professora Natália, da UF, que vai ser a chair da nossa primeira keynote. I would like to thank Natalie in advance for coming, for accepting our invitation. Thank you very much.
Hi people, it's very nice to have you all today here. This year we opted to invite 2 renowned women for speaking here at the SBSeg, and we are very proud to have Natalie Savanovic here today. She works at Google at Project Zero, and she researches vulnerabilities in extensions for web browsers. She's a hacker indeed, so if you have any doubts about anything about that, she's the girl for you to ask something related. And all the questions should be made after the presentation. If anyone wants to ask but is a little shy to ask in English, can ask in Portuguese, we translate for her. Okay? And Natalie, thank you again for being here with us.
Great. Thanks so much for inviting me to this conference. Yeah, thanks so much to everyone for actually coming and attending my talk. Today I'm going to talk about some of the research I've done into the security of browsers. My name is Natalie Silvanovic. Sorry. So I'm Natalie Silvanovic, and I I am a security researcher on Google Project Zero. So before that, I was on the Android security team at Google, and before that, I worked at BlackBerry. And most of my time I spent looking at browser security and mobile security. So today I'm going to talk about three different things. I'm going to start off by talking a bit about my team, about what we do and why we do it. And then I'm going to talk a bit about the features of browsers and two specific features, which are WebAssembly and WebRTC. And then I'll end off by talking a bit about what we can learn from this, and hopefully learn a bit about what we can do to make software more secure. So, Project Zero, our team mission is to make zero-day hard. So, you might have heard that as one of my recent projects, I have looked at 0 days in Adobe Flash. And this is two examples of recent 0 days that have been in the news. One of these is believed to be North Koreans who tried to access South Korean systems using a 0 day. And the other one of these is Middle Eastern countries, likewise using a malicious vulnerability to access people's data. And this is something that happens all the time. Many different actors, for many different reasons, decide to use O-days to compromise systems. And our team's mission is to, well, make that stop, or at least make it hard. And on the flip side, there are different ways that people get vulnerabilities. Sometimes they'll hire a dedicated team to find vulnerabilities, but quite often they will buy them from people. And this is a table from a company, Zerodium, that buys and sells vulnerabilities. And you can see this price table. This one, I think, is for the desktop servers. And you can see, for example, Windows RCE is like $300,000. So this is a lot of money. So these companies are paying a lot of money to buy 0 days, and you can imagine what people might be doing with them if they cost that much. And likewise, this is the mobile chart, and these are actually a bit higher. So this is a remote 0 day on iPhone. That goes for $1.5 million. And for example, there's a remote in iMessage, which I think is like $1 million. So, well, this does seem like a lot of money, and objectively it is. Our team feels that these prices are too low. Considering especially that people will find a couple of these and use them for a long time and use them to compromise a lot of people's systems, we think it should be harder for attackers to acquire 0 days. And one of the metrics of success we use is how much it costs to buy a specific vulnerability, and we want to help make systems more secure by finding these types of bugs. So we kind of have two parts of our approach. One is vulnerability research, and that's largely what I do. So basically our goal is to look at the systems that are attacked the most by attackers and try and find vulnerabilities in them so that they get fixed and those vulnerabilities are no longer available to attackers. The second thing we do is we work on structural improvements, on vulnerability mitigations and that sort of thing. And these are the features of software that make it more difficult to exploit a bug. Make it so that even if a bug does exist, it is more difficult, more expensive to get to a point where you can actually use this bug to access someone's system and get good results. So we kind of have a two-sided approach. One thing is to eliminate the low-hanging fruit. This basically means we want to get rid of all the really easy bugs to find, because we think those are the ones that attackers are likely to find and use the most. And we basically want to make it so that it's hard, if you don't have a lot of resources, to find a bug through fuzzing or find a bug through like really shallow code review. So this is one thing we do. We try and find these kind of first step bugs that are available to attackers and make it so that the barrier to entry to this first step in the chain is higher. And then on the flip side, we look at what we call the last step of the chain. And this is often things like sandboxes, things that are typically considered to be the hardest attack surface and the most difficult bugs for an attacker to find. And the thinking here is that the contention for these bugs is high. When you're talking about easy to find bugs, generally there's lots of them, so I think the probability that an attacker finds exactly the same bug and is actively using it is actually a bit lower. But when you think about these really high contention spaces with very few bugs in them, the probability that you find exactly the same bug that an attacker is using and close it becomes a lot higher. So those are the two things we focus on. We also I talked about the other side, which is not the vulnerability research, but mitigations. And we do a few things there. There's kind of, once again, two sides to it. One is review, and one is design. So to start off, we look at existing mitigations. These are features that are generally intended to reduce the impact of vulnerabilities when they exist. And these would be things like stat cookies, ASLR, those features that are used to reduce the exploitability of bugs. And we'll often document newly created mitigations so we know what they do, and we'll verify correctness. So often when there's a new mitigation, it hasn't really been tested in the real world, and we'll spend time trying to make sure that it actually does what the company thinks it does. And also, we'll discover edge cases. We'll often find things that weren't considered in the design of this mitigation and figure out, how much the mitigation actually affects exploitability, and we hope that we can give recommendations that help companies write better mitigations. We also sometimes have ideas for new mitigations, and this is the design side. So sometimes we'll perform exploit development, actually write full exploits for bugs, so we can see how you do it, and sometimes we'll even have ideas for new mitigations that can prevent this sort of thing. We'll also find points, we call them fragility points. These are places where an exploit is weak, where it's more likely to fail because of these problems. And we'll try and think of mitigations that make it even more likely it'll fail, to once again make it more difficult to attackers. And we'll also often share our ideas for new mitigations with companies that make software, so that hopefully they can implement the mitigations themselves. So I think my most frequently asked question about Project Zero is, how do we decide what we're going to look at? And this is actually fairly difficult, because ideally we would like to 100% look at the things that attackers target the most. But practically speaking, because attackers don't write us a letter and tell us every time they're attacking something, we can't find that out. So we try and use whatever we can see in the public to decide what to work on next. So this is often observed attacks, things that we've actually seen days of in the wild. Also, feedback from teams that observe attacks. Also things like that Zerodium chart I showed up front. Figuring out, based on the prices, what we think attackers are most likely to attack. And the things we focus on right now, which very well could change depending on where attacks go, is mobile. So we spend a lot of time on both Android and iOS. We also look at desktops, so Windows, OS X, and Linux. We also look at all 4 browsers, and that's what I'm going to talk about today with regards to my work. So that's Chrome, IE, Safari, and Firefox. And we've also done some work on document file formats and on antivirus. So now I'm going to start talking a bit about one specific project I've worked on, which is WebAssembly. And what I think is interesting about these 2 specific ideas of projects I've worked on is that they require 2 very different approaches. So when I started looking at WebAssembly, this was something where it was well specified, it had been recently written, and the standard was available, and the standard was actually followed. So my approach to this was to basically read through the standard and figure out where the weaknesses were, and then start looking for weaknesses. And then the other product I'll talk about, which is WebRTC. For WebRTC, I spent more time doing fuzzing and other testing activities because I didn't have as much information about how it worked. So, what is WebAssembly? Well, it's a format for writing assembly-like language on the web. So basically, you can write C++ or Java or whatever and use a transpiler, and then that will be used to write will be changed into WebAssembly, which can run on any browser. And there's kind of 2 motivations here. One, believe it or not, is security. So right now, when people need to do certain types of tasks, they'll often install a native application on their desktop. And that obviously has security implications because of all the things that a desktop application can do. But let's say instead you could write that application in WebAssembly and run it in your browser. Well, then the security impact of that would be a lot less. And then the other motivation is efficiency. So JavaScript is a weakly typed language. You can basically do anything to any data type and it will still work. So when you're doing something like addition, that actually ends up being very inefficient. Because let's say you're adding 2 numbers, well, the engine has to check are they both numbers and then add them, because you could also be doing string append with a plus sign, because you can also append 2 strings in JavaScript. So WebAssembly is supposed to be a solution for that. You can use WebAssembly to do math very quickly on a browser. You can basically add all the numbers together very quickly in WebAssembly and then call that from JavaScript. So compilability is a major goal, and it's doing okay, but it needs some improvement. So right now you can basically compile C++ and C very well in WebAssembly, and I think Rust is doing fairly well too. But then there are some languages, Java in particular, that you can't compile very well in WebAssembly, and this is because they have features like garbage collection that are very difficult to do in what WebAssembly provides, and I'll talk a bit more about that later. But the important thing to know is that WebAssembly wants to be compilable in every language. This is a very important goal of the committee that writes it, and I think over time there's going to be more and more stuff that can be compiled in WebAssembly. So it's a WC3 standard, and it has applications beyond browsers, believe it or not. I heard recently that the Ethereum interpreter is going to be implemented in WebAssembly soon, if it hasn't been already. So that's the sort of application that WebAssembly is going to eventually have in the future. So, why review WebAssembly? Well, number one, browsers are a frequently attacked target. I think a lot of 0 days are done in browsers, specifically because it's fairly easy just to convince someone to click a link. And it's also somewhat easy to write an exploit for a browser because it has so many features you can use in exploitation. And I also wanted to understand what the security risk of WebAssembly was, because I'd never seen anyone else review it before. And it also I thought it might be used by other software in the future, because the goal of WebAssembly is to eventually be run on the desktop. I thought it was a good opportunity to start looking at this before it's used for more stuff and the problems become more severe. So when you think about WebAssembly or any other language like this, there's actually two possible problems. Problem one is that engines aren't implemented securely. So your engine, when you run WebAssembly, it can corrupt memory. You know, you can put in some really malformed WebAssembly, and it can corrupt memory, and then that leads to code execution on your browser. And then there's a second problem, which is writing secure WebAssembly. Maybe there could be a vulnerability in an application written in WebAssembly, and then that causes problems. So, for this talk, I am talking about this problem, and I am not talking about this problem. But there's this talk at Black Hat. I think the video is available online, so if you're interested in the subject of writing secure code in WebAssembly, I'd recommend you look at that. So, what is WebAssembly? Well, it starts off as a binary, in a binary format, and because this is JavaScript, it's in an array buffer or a typed array. And you can load this using the keyword fetch in JavaScript, or you can just put every byte into the buffer like I did here. And then what does all this byte stuff actually mean? Well, it's in the WebAssembly binary format. And this is basically a format where there are a number of fields that have IDs and lengths and payload types. And this has all your WebAssembly stuff in that. And you'll notice, you know, there's lots of different types of fields. There is your function section that has all your functions in it. You've got your exports that have all your exports in it. And there are limitations on what sections your binary can have. For example, you need to have loaded a typed binary before you have the function section that actually uses those types in the function declaration. And likewise, there are some segments that are mandatory, and there are some segments that cannot occur more than once. And this is all enforced by the engine. Yeah, so here's the full list of the types, and I'll talk about what a lot of these are later. So the first step to parsing binary is to load this into what's called a module. So this is just the binary array, the array buffer, and you create the module, and then you have WebAssembly. And what could go wrong here? Well, there was this vulnerability that I found in Safari. And here's the problem. As I said, there are all these different sections in WebAssembly, and they have to be in certain orders. But unfortunately, on Safari, you could bypass the order check. You could put in a section which is called a custom section, and this is basically an unused section type that's available in case in the future WebAssembly changes. So right now, browsers are programmed to ignore this custom section type, and then in the future, if it's actually used for something, if they haven't been updated, they'll just ignore it, and hopefully the WebAssembly will still run. So when you process one of these custom sections, what would happen is it would reset all your order tracking. So now, if you put the custom section in, now you can put all the other sections in again, and the order doesn't have to be correct. And this caused a number of problems. What was actually cool about this bug is that some people found it independently of me and tried to use it to win a hacking contest called Pwn to Own. But they didn't succeed because I found the bug first and it got fixed, and then they ended up finding another bug to win. And they managed to actually exploit this vulnerability because a lot of the sections, when they were copied, they would actually not check the memory size because they assumed there was only one of each section. But this wasn't true, and that turned out to be highly exploitable. So, then there was this bug. This is kind of a typical bug, and it was in Chrome. And what happened is that they had basically an integer overflow only in 32-bit when they checked the size. So you can see this count plus type list size. If those are both integers, and if one of them is very large, then the integer, because integers are only 32 bits wide, can actually wrap around and become very small. And that's what actually happened here, and this was also a vulnerability. And then there was this vulnerability, and I thought this one was a little bit silly. It's also in Safari, and this is basically in JavaScript. When you create an array buffer, you can also create an int array buffer, and there's other types of like this, like 32-bit int array buffer. And they're what's called a view into the array buffer. So pretty much, you give it an offset, and then when you access index 0 in the int buffer, it's actually like, say, index 700, as in this example, in the real buffer. But the problem is that their WebAssembly implementation accidentally added this number in twice. And that's what I think, made this a surprising bug. So in this case, because they added it in twice, WebAssembly wouldn't work at all. If they ever use this feature, like it's not just a security problem, like WebAssembly would not work, it would not load the code, it would not do anything. So this means that basically they never tested this feature, otherwise they would have realized that it didn't work. But I guess that didn't happen, and there is this bug where you can basically index into the WebAssembly array, and then that's not a great bug, but you can at least use it to perhaps bypass ASLR when trying to exploit another bug. So now that we're done with creating this module, then you create something called an instance. And what the instance does is three things. It will load what's called an import, initialize an import, and create an export. So what are the WebAssembly imports? Well, there's three types. There is a function. So you can create a function in JavaScript or WebAssembly, and then load it into the WebAssembly instance, and then that's available in WebAssembly. You can call that JavaScript function from WebAssembly. And then you can also load memory, and I'll talk about that later, and you can load tables. And here's some WebAssembly terminology that you can use to impress all of your WebAssembly friends. So if there's a WebAssembly instance, and it has the same memory and the same table as another instance, they're called in the same compartment. And what you might be wondering when you see this is, can two instances be in half of the same compartment? Can they share the table but not the memory, or share the memory but not the table? And the answer to that is yes, in the specification they can. And there's no reason anyone would ever want to do this. No compiler would ever generate this code, but yes, it's allowed, and yes, browsers support it. So I guess this is, a little feature that is only ever used in vulnerabilities. So now what's this WebAssembly memory? It's basically all the memory that the WebAssembly uses. So the way WebAssembly is designed right now is you get a single page of memory, and that's all you can use. And then when you call a load or a store instruction, you just give it the index into this memory and it accesses it. And the way that you get more memory is that you call this function grow. So you initialize your memory, and this is the number of pages of memory, and then as you grow it, you can get more and more. So what could go wrong? Well, there's kind of two vulnerabilities I saw had been found in memory in the past. And what's kind of interesting here is they were both the same vulnerability pretty much on different engines. So this was a situation where I think there was a common error and the specification didn't clearly enough say how you should check for it. So the problem with both of these is that when you grow the memory, the integer that holds the size can wrap. Like with that locals issue in Chrome, if the integer gets too big, it goes around to 0 again, and then that is your memory size, except the engine still thinks that the memory is big, and you end up overflowing memory. So one question you might have is, can there be out-of-bounds issues in WebAssembly? And the answer to that is surprisingly no. when I looked at this, I thought at first, oh, I'm going to find tons of memory corruption issues where memory goes out of bounds. But I think it didn't happen for 3 reasons. One is that there's a limited and known set of WebAssembly instructions, and there's only about 6 instructions that access memory, load, store, and what's called T. So these are easily audible. It's easy to find them and check them, so I think that's one reason. Also, there is limited threading in WebAssembly, so I think that makes things easier. And then there's this other feature which I thought was really cool, which is called safe buffers or signal buffers. So what happens here is, as I said, the memory is 1 page, and it is 1 integer index that lets you go through the memory. So what they do on a 64-bit system is they map 4 gigs of memory. So that's the entire integer space. So from 0 to FF. And then they actually allocate the memory at the beginning for the amount of memory they want. And then when you move this index, it doesn't matter if you're in bounds or out of bounds. If you're in bounds, you'll get the memory. If you're out of bounds, you'll get a crash due to the unmapped memory. And then what's supposed to happen is that JavaScript will handle this exception and then give you like a JavaScript exception. What's cool about this is it's hard to mess it up. Because all of the memory is guaranteed not to be something that can cause security problems when you access it, then it's really hard to accidentally mess up this integer so that you can go out of bounds. And the other thing I think is really cool about this is it puts all the cost of bounds checking onto the person going out of bounds. Since this does no actual bounds checks outside of the exception, you can run super fast if you know you're going in bounds. And then if you go out of bounds, it's very, very slow. But that's not really a problem, because usually that's a mistake. Usually this code is not executing correctly if you're going out of bounds. So the other thing that you can load is called tables. And these are basically function tables. So you put functions into the table, and then you can call them in WebAssembly at that certain index. And once again, these kind of have a special feature for hackers. So you only need to change a table at startup. And you should never have to change it after you start the module. No compiler will ever generate that code. But once again, it's supported by the standard, so you can do it if you want to as a part of a vulnerability. And these are similar to the memory. You call this WebAssembly table create, and then you just call grow, and it makes them bigger. So what could go wrong here? Well, these are 2 bugs that were reported. One was in Firefox, the same bug as the memory, where when you expand it, they overflow the integer size, and then it actually gets smaller, but the engine thinks it got bigger. And then there's this issue which was found as part of the Chromium Vulnerability Rewards program. And it was in Chrome, and it was kind of an interesting bug in that it's in what's called 2 primitives, so toString or toInt on creating this table. Basically, if the index was not a number, but something with toString defined, you could then grow the buffer again, and the memory would be freed, but the system would think it would be allocated. And this is a fairly typical classic JavaScript bug. So that just goes to show, even though WebAssembly is its own thing, it's implemented in JavaScript. So any JavaScript vulnerability that could exist in regular code could exist in the WebAssembly bindings. So after this, what happens is initialization. So you've created your memory and you've created your table, but what if you want to start up with certain values in those? Well, in the binary, there are all those different segments, and there's data segments, and these are used to initialize memory, and there are element segments that are used to initialize the table. And this is another portion that I thought would be so full of bugs, just because copying memory usually doesn't get done correctly. But this was a case where they actually specified it very exactly in the specification. They specified all the checks, and this made it less likely to have bugs. So what could go wrong? Well, there was one issue that I found in tables, and this one just has a number, not a CVE, because I found it at the same time the Chrome team did, and they fixed it. So basically the problem is this. So you've got the table, and you've got the WebAssembly, which calls into the table, and then the table calls the function. But WebAssembly can call a JavaScript function, so you can get something where it's like, I have my WebAssembly, and it calls through the table to another WebAssembly function that calls into JavaScript. And what this JavaScript did is it removed the function that I was calling from the table. And this ended up being a use after free. Chrome wouldn't hold a reference to that memory, so once you got it out of the table, it was gone, and then you would access invalid memory as you unwound. But what was interesting is, so they fixed this. They fixed it so that if you are calling a JavaScript function from the WebAssembly function, it'll check the whole tree and won't allow you to change the table, which is fine, but then I had another idea. So remember those element segments that are used to initialize the table? Well, then I made it so that when I called my JavaScript, I would load and create another instance in the same compartment, and then it would initialize that table. And then once again, that would have the same effect of removing this function from the table, and once again, it would lose its memory because it didn't have a handle. So eventually, they fixed this so that there would actually be a handle to the function, even if it was removed from the table. And I think that was the right solution, and this bug has not come back yet. So anyhow, this is now at kind of the end stages of WebAssembly. In the end, you get an export. And once you get the exports, you call them, and then you can call WebAssembly. And now you've finished basically loading your WebAssembly. But one more thing, now it's actually going to run. So can there be runtime issues? And there can be, but I didn't find that many. One of them is instructions doing the wrong thing. And this actually did happen in early WebAssembly. If you look at the early engines, just as they were starting, there were lots of bugs like this, and some of them were security bugs, and some of them weren't security bugs. But they did happen, and I haven't seen very many of them recently, though. There's also a possibility of incorrect bounds checking, but for the reasons that I described in the memory section, I don't think that there's going to be very many of those. And then there were some issues, there could be issues with use after freeze, with incorrect handles, with memory being freed at the wrong time. And I think that's very much a possibility, though I didn't see any of those during my review. So, what about the future of WebAssembly? Well, I think they're actually kind of at a crossroads where things could go in two very different directions. One is they could kind of continue around the feature path they have now, and I think they are likely to have a limited number of bugs to be fairly secure. But then there's this other road where they keep adding more and more new features, and they become vulnerable to more things, and I think that would make them less secure. There's two features in particular I find concerning. One is concurrency. Right now, WebAssembly only supports the threading allowed in JavaScript, but in the future, they're considering making it so that it supports other threading. And I think in that case, that would cause a lot of vulnerabilities, because code that isn't thread safe would become code that needs to be thread safe, and I think it's unlikely they would make all those changes correctly. There's also WebAssembly GC, and this is a feature that is basically intended to make it so that you can compile Java in WebAssembly. And what this feature does is it allows you to ask for memory outside of the memory object, and then the engine is responsible for freeing that memory when you don't use it anymore. And I think this will break a lot of the good parts of the memory model right now. You won't be able to use signal buffers, for example, and that sort of thing. So I think this has the possibility of introducing vulnerabilities as well. But I don't know what the future is, and I don't know what's going to eventually happen to WebAssembly. So what can you learn from this? So I think one thing that's really important when you start running software, when you're creating new features, is to remember that design is important. And not just, like, a lot of people have a tendency to focus on things like crypto, on security features, And that stuff's really important, but what's also really important is the complexity of features. If you have a feature that's really hard to implement, that's really hard to test, that's very likely to have features in it, because that stuff isn't going to happen. And I think WebAssembly did this very well. It's an example of something that could have been very bad from a security perspective, but because they kept the feature set small and well specified, they didn't have as many problems. It's also a good idea to well specify features. That's another thing that WebAssembly really excelled at. They were quite exact in how things worked, and this made it so that there's less likely to be mistakes due to inconsistencies or people not doing checks they should. And finally, functional testing is important. I do a lot of security testing, but there was at least one bug in here that would have been solved if the people writing the code had done tests to make sure that the code does anything useful at all, and that didn't happen. So remember that security bugs are a subset of all bugs. So if you do ordinary things that will reduce the number of bugs in your software, it's very likely that it will reduce the number of security bugs as well. So now I'm going to talk about another piece of software I looked at that was very different from WebAssembly, but still in the browser. And this is WebRTC. WebRTC is the audio and video conferencing library in your browser. It was first implemented in 2011, but it didn't really hit most browsers until 2015. And now I think there's actually a lot of usage of it. So if you've ever logged into Facebook and used a video call, or even logged into Facebook and streamed a video, it's WebRTC that does this. It's a feature in the browser, and it basically allows people to stream video from anyone to anyone. So, why would I review WebRTC? Well, it had a large user base. When I started this, I knew it was used by all browsers, and I thought that would make it a good attack surface, because attackers often like these types of features where they can find one bug and it works in all browsers. Like, if you think of the WebAssembly stuff I did, let's say you were an attacker trying to find bugs in WebAssembly, you'd have to find a bug in all 4 browsers to have a bug that worked everywhere. But with WebRTC, theoretically, you'd only have to find it in basically one browser. And also, there wasn't a lot of public security information about it, and I thought that was interesting. So I thought it would be useful if I looked at it, even if I found nothing. I would be one of the first people to write about it and kind of make it that information available to other people. And then the thing that I found out later was that a very large number of non-browser applications use WebRTC in the Android client, and this would be Facebook, WhatsApp, Signal, Viber, Slack, etc., etc., etc. So it turned out the user base of this was even larger than I thought it would be. So how does WebRTC work? Well, there's 2 parts. You start off by doing what's called signaling, and this is not in the specification. It's actually not considered part of WebRTC. But basically, before you start WebRTC, you have to exchange information with the person you want to talk to make sure that you are using the same protocol, you're using the same codec, that sort of thing. And so you do this, and this, if you're a browser, this might be over WebSockets. If this is, say, a Facebook call, they probably send a Facebook message through Facebook. So you can use, any mechanism you have to send a message to the other person to get this started. And then there's the media. So once you've done the signaling, this stream is created between the 2 browsers, and it actually sends the video from the video call or whatever to the other user directly. And this also makes it a good target for attacks, because when you think about messaging applications, usually when you send a message to someone, it goes through the server, which means that they might restrict through the server what the contents is. But when you're sending something peer-to-peer, there's no way for them to restrict it. So it makes it less likely that a bug gets detected, and it makes it less likely that a bug gets filtered by the server. So here's another picture of WebRTC, and this is about the protocols. So on my right, maybe your left, the short one, is all the protocols that are used for signaling. So it's usually over TCP, hopefully they use TLS, sometimes it's HTTP, sometimes it's WebSockets. It can also be like a Facebook message, a WhatsApp message, you know, FaceTime, whatever they're using. And then after that, you create the actual streams. And for this, you usually start out over UDP, though I have seen the odd application that doesn't use UDP for this. And then there is ICE, stun, and turn. These are protocols that are used to find the other peer. So sometimes you're behind a NAT or other network infrastructure that makes it more difficult to send data from one peer to another, and this tries to find the best path. Then usually WebRTC is encrypted using TLS. And then there are two protocols, SRTP, which I think is encrypted another time, and SCTP. SCTP is less interesting. This is just used to send messages, like text messages, to the other peer if you need it. But what I think is really interesting is the SRTP. And this is the protocol that is used to actually send the audio and video to the other peer. So what was my first idea here? Well, my first idea was let's fuzz signaling. And here's why. Well, I thought, so I left something out of that first diagram. You have signaling, you signal to your peer signals back, and then you have to pick up the phone, or else nothing happens. And to me, it seemed like it would be a better attack if the person who you were attacking didn't have to pick up the phone. So I thought, you know, SDP vulns would probably be the best. So I tried this, and I did a few things. I used the WebRTC library, and I made a fuzzer that would, on the command line, basically send malformed data to this SDP parser over and over, and try and find bugs there. And then also, I reviewed the SDP code by hand, and I hoped to find a bug there. And this absolutely didn't work. I didn't find any bugs. And I also discovered in the process that some platforms actually implement SDP separately. So it turned out that Firefox, in particular, had its own SDP implementation that was different from Chrome's. And also Safari used Chrome's, but they kind of changed it a bit. So I felt that actually I wouldn't find a bug that worked on all the browsers through this. So I scrapped that idea and tried a different one. And so I started looking at the RTP and media protocols. And this does have the problem where typically you do have to pick up the phone. But I think actually that's not a big burden to say have to make a Facebook call to someone and they actually pick it up. And it also has a big attack surface. It has like many media protocols, many codecs and that sort of thing. And looking at the code, once again, I got a little discouraged because I noticed that they actually have fuzzers and OSS fuzz for every protocol and every codec. So they were actually fuzzing this all at scale. But I thought about, you know, what about end-to-end? What if one of these parsers parse the protocol and then gives something to the next parser that's not okay? Maybe that'll cause a problem. So I wrote an end-to-end fuzzer for this RTP protocol. So this took a few tries. I started off by making a prototype fuzzer, and this was just a fuzzer that I wanted to make quickly to make sure that this idea worked at all. So what I did is I altered Chrome to alter a byte of every 10th packet, and then I called another browser using this stream, and I found that this actually worked. In fact, my browser crashed every 30 seconds just by doing this. So that meant that there were actually quite a few bugs here. So I learned that the concept would generally work, and I got a few shallow bugs fixed. And some of these were security bugs, a lot of them were divide by zero bugs, but I kind of got it into a state where I could generally fuzz it pretty well. So I decided to go to the next step, and I wrote a C++ client that interacts with the browser. And this had the benefit, it ran a lot faster than the two browser instances, so I could find the big bugs a bit faster. It has the benefit it can run against any target. Is it a phone? Is it, Firefox? Is it IE? It could run against anything. And if I found a crash, it was guaranteed to work on the browser. So it was a very realistic representation of the attack surface. The con was it was super slow. So I found some additional end-to-end vulnerabilities in WebRTC doing this. And what happened next? Well, I found these bugs, and because I was using the two browsers or the client, all my repo steps were really difficult. They were all like, compile this client, compile the browser, go bury a frog in the woods at midnight, that sort of thing. And the developers of WebRTC got a little unhappy with me, and they were like, oh, we have an emulator that you can use to emulate WebRTC, and what you should do is you should record your stream and replay it. So I tried it, and it didn't actually work, but I played with it a bit, and I added some extra code to make it actually work so that it could reliably reproduce a stream from the browser. And this was a good way to test because it was extremely fast and extremely portable. I could compile this on Linux, I could send it to multiple cores, I could even compile it with things like asand that make it so that memory corruption crashes right away. So this was super good from that perspective. What was not as good about it is that it's not an exact representation of WebRTC. So there was no guarantee that any bug I found on there would work, and I would have to test them and make sure that they were actually okay on the browser. But it worked, and I found many bugs using that. So I finally had something that mostly worked for this purpose. So what happened? I found 7 vulnerabilities, and this is the first one. And I'm actually hoping that everyone in here could take a look at it and try and figure out what the problem is. I'll give you a minute, and put your hand up if you think you know what the problem is. And feel free to even guess if you want. So, any guesses in the back?
It's just a guess. I guess the current SS index is not unchecked, so you could like auto-bounce it. I mean, I'm just assuming there's this calculated structures, and there is no, it's using the current SS index, and if the user has control over that, you can use that.
So I'm going to explain what he said so that everyone can hear it. So he said that the current SSIDX, so could go out of bounds, and that could cause a security problem. In this case, that's actually a trusted value, so that's not the problem here, but that is a common problem, and I'll show you one like that after this. Any other guesses? In the front?
Maybe if you try to send a string with a lot of keyframes, you may have a DOS. You may have a DOS if you have a string with 0 keyframes.
Yeah, I'm just thinking that's another problem that is probably a problem in this code. Yeah, I didn't test for that sort of thing, but maybe I will now. But yeah, that was not the specific issue here. I'll show it to you here, and Like, don't worry, I was very surprised by this bug. I had never seen a bug like this before, which is why I thought this was a fun exercise. So, you call find, and one thing I've never considered is what happens if you call find on a map and it doesn't find anything? Well, it returns this end value. And what that does is that actually points to the very end of the buffer. So if this is the end of your buffer, it points right to the end of it. So if you write to end, you're going to write out of the buffer. And if you read from end, you're reading out of memory that's not a part of your buffer. So this ended up being a vulnerability because this would end up being out of bounds, and then this info was in unallocated memory. And yeah, I was not expecting that. I thought it was kind of an interesting bug. And this is the benefit of fuzzing. Even if you don't understand the bug, even if you weren't expecting it, you can find bugs using it, and maybe even bugs you don't expect. So there were some other interesting bugs here. So this is another interesting one. It's a use after free. So this one is, so goofinfo is a vector, and lower bound in a vector just strips everything out of the buffer that is lower than the lower bound you provide. But this one was actually untrusted, pulled directly out of the packet, so it can be anything. And if it's really high, you just pull everything out of this buffer, and now everything has been freed, but you're still using that info you pulled out, so that becomes a use after free. This is the one that's similar to what Lucas described, which was that you go out of bounds. And this is a situation where you have this ID at the top, and then you do the loop, and you make it sub L, which is the value, and it goes up to the max of this buffer, which I looked up, and it was 5. But then where does it come from? Well, they read 3 bits, and 3 bits can go up to 7. So you can actually write 2 values, or read 2 values that are out of bounds. And then there's this bug. I really like this bug, once again, because it was so unexpected. So there's something in WebRTC that's called forward error correction that fixes up your packets if they get lost. But theoretically, according to the standard, 1500 bytes in a packet of FEC. So it just blindly copies everything off the wire into this packet. And, so let's say it's a 2000 byte packet, it just gets copied. So this ended up being a huge controllable buffer overflow using memcopy. And I'll admit I wasn't expecting to find a bug like this just because it was so simple. But once again, that is what I found. There were also 2 bugs in decoders. Neither of these are, I think, that great in terms of exploitability. But there is this use after free in VP8. And what was interesting about this is a decoder that's used for a lot of things that aren't WebRTC. So that bug had a higher impact because it impacted more things. And then there was this untyped confusion bug. And that one, it was kind of interesting in how it happened, in that if you were using one decoder, but then your stream looked like it was H.264, there would actually be type confusion because it wouldn't be quite sure what type it was. But this ended up just being an out-of-bounds read. But wait, there's more. The other thing that I found out about WebRTC, which I hadn't known when I started looking at it, it was just how heavily used it was. So this is a statistic I completely made up, and I have no way of knowing whether it's true, but I think it's probably true. And that's that I think everyone has 3 or 4 implementations of WebRTC on their phone. So every one of these messengers has an embedded copy of WebRTC in it, and that's, not a central copy, not an Android copy. It is just a copy they compile themselves, and there's no patch strategy. And what was even worse is that WebRTC, if you look at their website, there was no guidance on updates. There was no way to find out whether, your version was up to date or you needed to update it. So I found it really concerning that this was just such a widely used piece of software, and there was no history security bugs, no way to file security bugs, and no way to update security bugs. So I worked with the WebRTC team to fix this, and now they have guidance on their website, and they release a list of bugs every month and that sort of thing. But I was surprised to find that on something that has such a big user base. So, WebRTC fuzzing. I committed this, I had my fixed version, and the developers said my code was not up to their coding guidelines, so they rewrote it and they implemented it to the WebRTC repository. So it's called Video Replay, and you can try this at home, and that's what I'm hoping will happen. This tool is now available to everyone, and you can use it to fuzz WebRTC, and you can use it to test vulnerabilities in WebRTC. So what did I learn here? End-to-end testing is important. They thought they tested this. They had fuzzers written for every single protocol, every single codec, and that wasn't enough because they didn't test the whole thing together. So that's important. Also, I think it's important to consider patch strategy when you design things. I think this is something I found in this project, that even between the browsers, there were patch gaps, and among things like Facebook Messenger, things weren't perfectly patched, and that's something that I think they should have thought of as soon as they started making WebRTC, because these things are harder to fix late in the game. And finally, it's a good idea to kind of reevaluate your user base regularly. So how it started was WebRTC was intended for Chrome and other browsers, and then it took off. So believe it or not, Chrome is no longer the biggest user of WebRTC. Number 1 is Facebook, number 2 is WhatsApp, and number 3 are browsers. So I think it's important, if you are making software that can be used by other people, even if you think your user base is this one group of people, make sure that 5 years later it hasn't changed to be something completely different. And even more conclusions here. From this overall project, I learned that there were actually things in the browser that didn't have a lot of attention, and I wasn't expecting that. But I guess the truth is that a lot of people who are into browsers, they worry about JavaScript, they worry about HTML, and they don't spend as much time thinking about these little features like WebAssembly, like WebRTC, like, I don't know, WebBluetooth, that sort of thing. But, a bug is a bug, and attackers can find bugs anywhere in the browser. Also, it was interesting, the different bug finding techniques worked differently on different targets. For WebAssembly, I think going through the spec was the right thing. WebRTC was far too big to do that, and fuzzing ended up working well. The other thing is that there was a lot of tooling effort in both of these projects. I had to invest a lot of time before I found any bugs, and in both of them it turned out to be worth it. So I'm glad I did that, and I think what I learned from that is even if you're not sure you're going to find bugs and something's a lot of effort, it's usually worth doing it just to find out. And then finally, I've talked about this before, but yeah, both of the projects do kind of have patching strategy problems because they are things that are originally in browsers and because they're becoming things out of browsers, like for example Ethereum for WebAssembly and all these messengers for WebRTC. So once again, it's important to think about this stuff before you make a library and make sure you keep up to date on who's using it. So that's it. Well, I have some time for questions now, and then afterwards, if you have some time, I have a couple of bonus slides about WhatsApp. So about questions, if you're too shy to ask in English, you can ask in Portuguese, and Natalia will translate. Also, if you're still too shy, I have my contact info there, and you can ask me online.
Some questions?
It's about WebAssembly.
Sure.
Right, so, okay, first off, it was a great talk. Right, and I'm just wondering, if you could elaborate, on the kinds of seeds that you use for fuzzing on WebAssemblies. Right, what kind of, we have like a regression suite that is used for this fuzz, those inputs, and also what kind of fuzzers are you using? Like
Yeah, so for WebAssembly, fuzzing wasn't very effective. So I tried fuzzing, and we have a tool we use internally at Google, but pretty much how it works is that you have a target, you build the target on Linux, and then you build it with ASAN, which is a tool in Clang that allows you, basically, it does memory sanitization and will make it more likely to crash and crash consistently if there's bugs in it. And then we have basically fuzzing algorithms that we use, but I would say none of them are very complex. They're mostly things like flip a byte, flip a bit, skew random data, that sort of thing. But then we also have coverage hooked in. So when you build with ASAN, you can do ASAN coverage, and that allows you to get data about what code has been hit. And so then when the fuzzing happens, it will load a template and it will fuzz it. And if that case, even if it doesn't crash, results in increased code coverage, then that template will be favored and will continue fuzzing more with that template, once again favoring things that increase code coverage. So that leads to a lot more efficient fuzzing. Did that answer your question?
What?
Actually, I have two questions.
Sure.
The first one is, did you try to exploit any WebRTC code?
Sorry, what?
Did you try to exploit any WebRTC code?
No, I didn't. I haven't actually tried to exploit any of the bugs in this presentation.
Okay, the second one is more related with script engines like JavaScript.
Sure.
So when you are doing code review, actually when you have a target like Firefox, Safari, or anything like that, how do you decide if you are going to do code review or fuzzing? Like, do you just wake up like, today I'm gonna look in JavaScript arrays and I'm gonna find a lot of zero days to code review? Or you do fuzzing, and if you do fuzzing, what kind of technique do you use, like rotation fuzzing, generative fuzzing, or something like that?
Yes, so, like, I would say, like, I don't have a super clear process that's 100% effective, but it's more, I get a feeling about different things. I would say for things that are well specified and have limited entry points, I tend to like to use code review. Almost all my browser bugs I find through code review, all my JavaScript bugs. Also, I found a number of bugs in Adobe Flash. Almost every single one of those was code review. And the reason I did that was twofold. Some things, especially like JavaScript, are actually quite difficult to fuzz. Like, it's hard to find all the features and make something that will generate all the features and actually load it into a script engine so that it'll actually run. So, but for code review, it's quite easy to go through like every JavaScript function in the spec one by one and look at it. So I think that makes it easier. Meanwhile, something like, say, a media file, that's something that's quite easy to get a media file that uses all the features. Meanwhile, the code is way more complex. And like the specifications are like too complicated for a human to understand. So that's kind of how I make the call. And this is the same thing with the WebRTC. Like, I definitely met people who understand it, but I think the ramp up to get there it is very long. So that's why I decided to fuzz it.
Perfect, thank you.
Over there.
So I've got a more kind of philosophical question. I've seen from the bugs that you mentioned, that you exemplified, new techniques, quite sophisticated ones. It would be very hard to spot. But also things like, very simple buffer overflow. It's a whole range of vulnerabilities. Some known, some very hard to spot or to even imagine. My question is, what's the way forward? Should you scale your Google Project Zero everywhere to all kinds of development, software development? Or is there something that developers are missing?
hard question. What I would say, if there's something that, well, like you're basically being like, hey Natalie, can you solve security right now? But the thing is, so if developers are missing something, we don't know what that is. And I don't think anyone has a clear answer to, what is the thing we can do that would make everything 100% secure and avoid, any security problems. I mean, what we're trying to do with Project Zero is replicate what an attacker does and try and find similar bugs for the dual purposes of making those bugs not available, but also creating a body of knowledge so that we know what attackers are capable of. And I think we've had success with our specific mission, which is to make the targeted O days hard, but I don't think that that is the only security problem that needs to be solved. Very far from it, and it's definitely not the only solution. So I think what we're doing is effective at one specific thing, but I think that there are many other things that need to be done to secure software. Did I answer the meaning of life?
I would say, building a library of knowledge is good, but it's very hard for the developer to think about all the possibilities in his mind while he's writing code.
Yeah, so I've actually gone to companies and given talks to developers, and I think the one thing, if I had one thing that I wanted a developer to learn from this, and I snuck in a few times, is a lot of these bugs are needless attack surface and needless complexity. I think if there's one thing a developer could do, it's to not have as many features if they're not being used, and make the features simple. Because many of these bugs, I would say, both in WebRTC and in WebAssembly, are due to things that had no value to the user and limited value to the developer. So I think if there was one thing, it would be keep features simple and necessary. So any more questions?
Just one question. This is for Bob first. And I was wondering if when we are using WebAssembly and we load two modules using the same space of tables and memory, are you creating a kind of side channel attack? Because one module can read the memory of the other.
Yeah, so it's funny. I know a guy who's obsessed with that topic, but so the idea right now is that you're not supposed to do that. That if you have two WebAssembly modules that are basically using the same memory and the same table, these should be ideally modules that you both wrote, that you wrote, or that you trust. And this is not something that you should be able to do with untrusted modules. And I do know people who are working on the problem of, when WebAssembly becomes used enough that there's lots of libraries online, how are we going to make this safe? And I don't know what the answer is, but this is something that I think the committee is considering. But yes, I do think that'll be a problem if WebAssembly is ever used in that way. In the back.
Thanks for the talk. From a backend standpoint, what should be the ideal breakpoint between insights and the body of knowledge for searching this kind of bugs?
Sorry, can you say that again?
What's the ideal standpoint or breakpoint of the knowledge and the insight you have while you are looking at the code? Okay.
Yeah.
Are you hearing now?
Yeah. Yes,
Okay.
yes, sir. I'm not sure what you're saying.
Because much
much of the time I was looking for bugs in the code. So you have to get really into the code to see what kind of bugs.
Yeah.
And kind of some of them you have to just look at the CVEs or knowledge bases to really get one easily. So what's the kind of breakpoint between those type of knowledge?
Yeah, I guess like I focus most of my time on analysis, and I mostly spend my time looking for new bugs and looking at source to understand stuff myself. But I don't know if that's always the best approach. But I think like if you're doing what I'm trying to do, which is kind of find bugs that maybe there isn't a lot of documentation about and that sort of thing, like I think that's the approach that works.
Okay, thanks.
Any more questions? Last chance. Okay, I'm going to move on to some bonus slides here, and after those ones you can also ask questions. So let's talk about WhatsApp. So I've been working on WhatsApp for a bit. So after I did the WebRTC thing, I started thinking about the other implementations. And WhatsApp does use WebRTC, but they don't use all WebRTC. They actually also use a competing implementation called PJSIP, which is open source, but it's commercial. You usually have to pay to use it. And I wanted to see if I could find any bugs in WhatsApp and try and get a feeling, did these bugs just happen in WebRTC or could they happen anywhere? So, unfortunately for this one, I had no symbols, I had no source. So I decided I'm going to look at the Android app, and this was because Android debuggability is much easier than iOS debuggability. And even though there wasn't symbols, I knew that PJSIP used an open source RTP library made by Cisco called libsrtp. So, and I also had the source to PJSIP. So I went through, and based on log entries, I found a mem copy that copied the unencrypted packet into a new packet. So my first idea was, let's hook this mem copy using something called Frida, which is a tool on Android. It's actually really cool, and it lets you hook stuff fairly easily. And this kind of worked, but it was too slow. Phone calls, there are like a lot of frames going every second and a lot of mem copies going on, and this made the call stutter too much. And also the thing about WebRTC is if you start going slower, the system starts changing. It will realize you're on a bad connection and start doing different things, and I didn't want that to happen. So I scrapped this, and I realized I was going to have to just alter the source or the binary of WhatsApp. So I changed the mem copy at that specific point to point to just a function I wrote, and I wrote this function in assembly where the GIF transcoder was. And what this function did is it DL opened a path on my Android device, and then it loaded a function from it, and then it called it. So one thing that was really helpful is I discovered there was an online ARM branch calculator that really helped me make sure I was calling the right things. And then after a lot of failed times, this eventually worked. And then I had some issues with calls disconnecting, and it turned out I had this wrong again. I was corrupting a register. But then I finally got it to work for real, and I was able to, in this library, if I wanted to log every packet incoming, I could do this. I could also copy them back into the next set of packets and replay them. So I tried that, but the problem is just copying them into the new packets didn't work. So I discovered that WhatsApp has 4 RTC streams. So when I was looking at WebRTC, this wasn't a problem because I had the source, and I could try a video stream, I could try an audio stream, one at a time, and it was fine. But WhatsApp, they have like, I don't know, I think it's like one stream for video, one stream for audio, one stream for synchronization, and like one stream for good luck. So they had 4 of them, but luckily they all had payload types I could recognize in the packets. So I made it so that when it replays, it checks the type of the packet it's sending, and if it's the right type of packet, it will put the new thing in. Otherwise, it will put one of the other type in. And then there's also this thing called the SSRC in RTP, and that's basically a random number that gets generated every time you create a stream. And that's so, like, if you have like 17 video call windows open in Facebook, you can keep them all straight. So I had to basically figure out what the current one was and copy it in when I was replaying the stream. But this eventually worked. So then I replaced the function with a fuzz function. So now when you mem copied, it would change a byte, or it would lengthen or shorten your packet. And we were talking about coverage. Well, there's like absolutely no coverage here because I'm just like on a phone sending a corrupt stream to another phone. So this was like kind of not very advanced fuzzing, but it was like what I could set up considering what I have for WhatsApp. So I did this, and it took 15 minutes to crash, and it was a heap corruption bug, which I filed to WhatsApp, and WhatsApp fixed it actually very quickly. But this is, like, I found a bit of a concerning bug, because anyone can call anyone on WhatsApp, and you do have to pick up the call to reach this bug. But other than that, I think it's actually fairly likely that this bug could be exploited by an attacker. So what did we learn here? So test end-to-end, and also evaluate third-party products and implementations. I actually don't know where this bug came from. It could be a bug in PJSIP, it could be a bug in WebRTC, though I don't think it is because I didn't see anything similar in my analysis. Or it could be a bug in how they used WebRTC or how they used PJSIP. So I think even if you're just using a third-party product, it's important to evaluate it and also test your own implementation so you know that you didn't integrate it wrong and cause problems. And then my final thing to remember is crypto isn't not enough. So when everyone talks about WhatsApp security, they talk about crypto. And I think like that's a very important area to make sure that people can't read your messages after you send them. But it's not enough if people can just send you a bad message and get memory corruption and then get code execution on your WhatsApp and read all your messages anyhow. So it's important when you look at software to have a holistic view and think of all the types of attacks, not just crypto or whether people can read your messages on the wire. So that's it. This is really the end of the talk, and I'll have more time for questions if you're interested.
Questions? Last time. So we would like to...
Sounds good. Thanks a lot.
We would like to thank you a lot. So, pessoal, a gente gostaria de avisar que o ônibus vai sair às 18h40 lá de baixo. Então, eu vou pegar.
Sim, deixa eu só... Pessoal, agora, só lembrando que vai ter a assembleia da Comissão Especial de Segurança da